Okay, this section is actually fairly short, but it is, at least I would say the first slide is extremely valuable. I kind of hinted at what the first slide is going to be. If it wasn't last lecture, the lecture before, when we were going through that very complicated example with substitution. And so this is a very special form of factoring, and it seems like it's almost so niche that you would never see it. If you have something that can be expressed in the form of a squared minus b squared, so for example, x squared minus 4, that would be a pretty common one, then you can factor it immediately. You don't have to go through the whole process of multiplying to get the last term, adding to get the middle term. In this case, you can just write it as kind of the square root of that first term. So a plus b times a minus b. So that's the a is the square root of the first term. So if I have x squared, that would be x. And b is the square root of the second term. So if I had 4, my b would be 2. So even though it does seem specialized, we see it again and again and again because it does show up in many different places. It shows up when we talk about circles. It shows up when we are trying to factor fractions. And so it is kind of worth, I'm very much not a fan of memorizing formulas. I would probably memorize this one. This one will save you a lot of time for you to quickly just identify this simple case and spit out the actual factors versus having to go through the process again and again. So here's a list of squares to kind of help you recognize when to use this. Because if it's not in this exact form, you can't really do anything, or you can't at least do this formula. You can't use your difference of squares. So to help you recognize, this is kind of just a table of the perfect squares up to 10. So 4 squared is 16, 6 squared is 36, 9 squared is 81. I imagine most of you guys have seen this before. Several of you probably have it memorized, but it's worth kind of having a refresher. So all of that long-windedness to go straight into an example now. So I have x squared minus 49, and so I've seen a lot of problems, so maybe this is why my head automatically kind of thinks about the formula, but what you should be looking for, or what kind of should tip you off to say, okay, maybe I need to use difference of squares, is 1, you're going to have 2 terms. 2, usually your first term is x squared. That's not always true, but usually your first term is x squared. And so really kind of the biggest thing to check for is the second term squared. And also, is there a minus in the middle? If there's a plus in the middle, we can't use difference of squares. So kind of have that checklist cooking. And in this case, yeah, I have x squared, my first term. I have a minus in the middle. I have 2 terms. And my last term is 49, which 7 squared is 49. So that is a perfect square. And so then once you recognize those things, then you just use the formula. I take the square root of 49. And so I have x plus 7, x minus 7. And I'm done. So like I said, the first couple times you see it, kind of walking through that mental checklist seems like a lot, but really it makes it a one-step question when you can recognize that. So here again, I see a minus, I see 2 terms. So already my brain starting to get a little bit in the thought process of thinking difference of squares. And now we just got to kind of look at both terms. Okay, I have 4y squared, 2y gets me 4y squared, check. 16x squared, take the square root of that, I get 4x. And so now so my a is going to be 2y, my b is going to be 4x, and so I'll have 2y plus 4x, 2y minus 4x. And honestly, that's kind of a good way to think about that, is identifying your a and your b, because once you have it, throwing in your formula makes your life easy. So that's maybe what I should have done in that first example, but now we have another one here. I have x to the 4th minus 81. So it seems like we have that minus, great check. We have 81, which is 9 squared, also nice. And x to the 4th. So it doesn't seem like we have something squared in the first term, but that's kind of deceiving. And that was an issue on the previous lecture of thinking, well, actually the square root of x to the 4th is x squared. And so my a is going to be x squared, my b is going to be 9, and I just throw it in the formula. X squared plus 9 times x squared minus 9. Now, that's a good first step, but notice how I still have a square lingering. So as long as there's something squared going on and two terms and a minus, I should try and keep going. I should try and keep factoring if it's at all possible. Sometimes it's not. Like in the first two examples, we did difference of squares and we're good. But in this case, if we look at both of those parentheses, the first one has x squared plus 9. So that's meeting a lot of my requirements, except I have a plus in the middle. So I can't actually use difference of squares on that. In fact, I can't really factor that without using weird imaginary numbers that we're not going to worry about. But for the second parentheses, I have x squared minus 9. Okay, well, square root of x squared is x, so that's something squared. 3 squared is 9, so that's something squared. And I have a minus in the middle. So my a is going to be x, my b is going to be 3. And so I can factor that second parentheses, x plus 3 times x minus 3. And then I just bring the first parentheses over it. I can't factor that any further. So that's one of the errors that I see, is sometimes we try and force this formula because once we get comfortable with it, it is pretty nice, but I have to have a minus between my two terms. If I don't have a minus, I can't use the, looking at the title, the difference of squares formula. Now this one, I would say might be a little bit less important for the fact of when I kind of look back at formulas and I'm developing lessons, if I have kind of a formula stuck in my brain, that probably means that I used it a lot and it's going to be valuable for the future of your guys' math careers, and it's worth really focusing on. And this formula falls into the category of I kind of have to look it up. And so what that means is it doesn't really come up that often. I wouldn't say it's anywhere near as valuable as the previous slide. That being said, it is kind of a nice formula if you can see it, and I wouldn't fully rule it out for the next exam. I might kind of emphasize that more once I actually can see the exam, but yeah, all that's to say is that this slide, although isn't an entire waste of time, is not going to be as valuable as the previous one. And so with difference in sum and difference of cubes, in this case, we can have a plus in the middle or a minus in the middle. And depending on which one of that is, that kind of determines what formula you're going to use. So the first one is x cubed, or a cubed plus b cubed is going to be equal to a plus b times a squared minus ab plus b squared. The second one's pretty similar. And kind of the key to this one and the previous one is identifying your a and your b and kind of going from there. And so if this question shows up, you're not going to deal with a cube that's bigger than 5. We're not going to hope you can recognize 7 cubed, because honestly, I'd have to sit down and think for a little bit about what 7 cubed actually is. That's not something I would probably instantly recognize when it's put in front of me. So with that in mind, this is kind of the list of cubes that we would expect you to know and kind of recognize if a question like this showed up. So 1 cubed is 1, 2 cubed is 8, 3 cubed is 27, 4 cubed is 64, and 5 cubed is 125. And in all reality, those are pretty valuable. You see those show up a lot in math. These particular cubes come into a lot of examples, so it's a good thing to have these in your back pocket. So to see as an example, I have x cubed plus 27. First thing, can I use difference of cubes? Are both of my terms something that's cubed? Well, x cubed is x cubed, as weird as that's to say, or x times x times x is x cubed. So my first term is something cubed, x. And now my second term, looking at my chart, I see, oh, okay, 27 is 3 cubed. And so both of those are cubed. I have 2 terms. That means I meet the requirements of sum and difference of cubes. And then the last piece I have to do is just identify which formula I'm going to use. So I have a plus in the middle. So that means I'm going to use the first formula. I got to identify my a and my b. My a is x, and my b is, it's going to be the cube root of 27, or 3. And now I just throw things in the formula. X plus 3, x squared, minus the tiny bit of math that we occasionally have is being careful with squaring, and additionally making sure that you do a times b. So my a is 3, my b is, or sorry, my a is x, my b is 3, so I get minus 3x plus 9. Now, in this problem, I have two terms. I have a minus in the middle, and it looks like one of my terms at least has a cube in it. So I should be tipped off. Maybe I'm using some indifference of cubes. And in fact, y times y gets me y cubed. And then looking at my chart, oh, now I see that I don't actually have any cubes. And so I kind of made a mistake that I mentioned last time should actually always be your first step. And that's to pull out your GCF. So sometimes, and this happens with difference of squares too, sometimes it looks like you're really close to be able to use these formulas, but you kind of fall up short because maybe you don't have an exact cube or something like that. So if you pull out a GCF, in this case, 2 fits into both of your terms. Now I have something that is cubed minus something that is cubed, and now I can use my formula. So as I mentioned, the first part of my first term is going to be, if I take the cube root, is going to be y. And then looking at my chart, the cube root of 8 is 2. So a is going to be 2y. And then the cube root of 125 is 5. So my b is going to be 5. And then I just fill in my formula. I will get 2. I got to bring my 2 over from the first step. I'm going to use my second formula. And I just fill in my a's and my b's. So 2y minus 5 times 2y squared, but make sure you kind of put a parentheses around that 2y. So that would actually be 2y times 2y, which gets me 4y squared, plus a times b. So my a was 2y, my b was 5, I get 10y. And then b squared is going to be 5 times 5, or 25.